What actually happens to an object falling into a black hole? The answer defies almost every intuitive understanding we have about reality. Our instinct is to picture a cosmic vacuum cleaner, sucking up everything in the neighborhood. But from a safe distance, a black hole's gravity behaves like any regular star of the same mass. If we replaced our sun with a black hole weighing the same amount, Earth would keep orbiting right where it is. The defining difference lies in density. A black hole is an enormous concentration of matter packed into an unimaginably tiny volume. It is a region where mass dominates the fabric of spacetime, creating an inescapable gravitational trap. The outer edge of that trap is a boundary known as the event horizon. As you move closer to all that concentrated mass, the velocity required to escape its pull climbs higher and higher. The event horizon is the exact mathematical radius where the required escape velocity exceeds the speed of light. Since nothing in the universe travels faster than light, nothing passing this threshold can ever return. A black hole cannot emit or reflect light, rendering its interior permanently invisible to outside observers. There is no solid ground to crash into here. The event horizon is a one-way boundary severing everything inside from the rest of the universe. Approaching that boundary exacts a severe physical toll. Due to the extreme density, the difference in the gravitational pull across even short distances becomes incredibly sharp, generating intense tidal forces. If you were to fall feet first, the gravity tugging at your leading edge would be vastly stronger than the force pulling on your trailing edge. You would be stretched vertically into a long, thin strand. Simultaneously, the geometry of the gravitational field forces you inward from the sides, crushing you horizontally, as if you were being squeezed like a tube of toothpaste. Physicists refer to this mechanical distortion as spaghettification. The timing of this destruction depends entirely on mass. A stellar mass black hole has a tight, violent gradient that will shred an object long before it reaches the event horizon. A supermassive black hole, however, has a much more gradual incline, allowing an object to pass the threshold intact. Physical survival through the boundary depends on the size of the black hole you fall into, even if the ultimate trap remains inescapable. This physical crushing is accompanied by a severe distortion of time. The immense mass curves spacetime so drastically that the passage of time itself becomes relative. To an observer watching from Earth, an object falling toward the event horizon appears to slow down. As the light fighting against the gravity loses energy, it stretches into dimmer, redder wavelengths, eventually freezing completely at the edge. The distant observer never actually sees the object cross over. Yet, for the observer actually taking the fall, time passes normally. They cross the event horizon in a finite amount of proper time, their own watch ticking at a steady, uninterrupted rhythm. Relativity dictates that there is no universal clock. The reality of the descent depends entirely on the frame of reference you are measuring it from. If no light escapes this boundary, how do we know these structures exist anywhere outside of mathematical theory? This 2019 Event Horizon Telescope image provided empirical proof, the N87 black hole casting a dark shadow. The bright asymmetrical ring is the accretion disk. Gravity warps the light, and Doppler beaming makes the bottom region, rotating toward us, appear far more luminous. This grid displays the synthetic images generated by astronomers to test their theoretical models. When they compared the real observation against these simulations, the match confirmed that general relativity accurately predicted the shadow's shape and scale. We also gather evidence through tidal disruption events. When a star wanders too close and is torn apart, observatories track the resulting intense X-ray flares as the stellar debris heats up and spirals into the void. By directly imaging the shadow of an invisible object and watching it consume nearby stars, we moved black holes out of pure mathematics and into verifiable astronomical reality. Now we must cross the event horizon, leaving observable reality to explore what the mathematical models predict lies at the dead center. General relativity points to the singularity. It is the theoretical destination where all infalling matter is crushed to an infinite density, occupying zero volume. But an answer of infinity in physics usually indicates a mathematical error. The prediction of infinite density likely signals the exact point where our current equations of general relativity break down and stop working. To understand the true physical reality of the interior, we would need a yet undiscovered theory of quantum gravity, a framework that can unite the physics of massive gravitational fields with the microscopic rules of quantum mechanics. Black holes represent the terminal physical boundaries of human knowledge, marking the exact coordinates where the next revolution in physics must begin.